Let's see. Okay, and we're live.
Welcome everyone to the MSR 2020 Ask Me Anything panel. And now I have to turn off something. If I speak, is there an echo with other people?
No.
Okay. We have a distinguished group of panelists. One of the challenges in the virtual world is that we lose the interaction in conferences where people can have that one-on-one of anything. So to repair that, we've created the Ask Me Anything format. We have some distinguished speakers who will talk to us about their stuff. I've asked them to introduce themselves with 4 minutes of talk. And then what happens after that is really up to you. We have a Slack channel where you can ask any questions at all. I'll moderate the questions, and then we'll just see where the conversation goes. So please consider this as a community effort where what we do is a function of what we all put together. So Christian, if we go to our first slide, please. Here are our panelists today. I'm going to ask them to introduce themselves in 30 seconds. In order of these four boxes, please.
I can start. All right, cool. My name is Mohammed Al-Geish. I'm Director of AI at Cisco. And before that, I was co-founder of a company in AI field called Voicea that takes minutes for your meetings, such like this one. Co-authored a book called The Competing with Data that talks about the skill gap between statisticians and folks who are coming from very clear academic background on how to deal with data, and practitioners who are dealing with big data at scale. I also do TA at Stanford, deep learning specifically.
Should I go, Christian? Okay, I go.
Yes,
so my name is Futka. I'm professor from Polytechnic Montreal, where I do research on software engineering, mining software repository, and very recently have been doing a lot of research on the engineering of machine learning-based systems. So as you may know, Montreal is a big AI hub. So we have a lot of people producing a lot of AI and machine learning algorithms, and many companies trying to consume them. So it was a bit natural that we had this thematic picking up here in Montreal, and we started looking at the challenge of bringing all those AI-based systems in production. And I've been running similar with my colleagues from Polytechnic for 3 years now, and yeah, that's about me for now. Yeah.
All right, I'm Christian. I teach software engineering at Carnegie Mellon and do research on a bunch of topics like product lines and open source. And I think relevant here is that I'm teaching a course on software engineering for AI-enabled systems.
Hi, my name is Miriam Kim. I'm a professor at UCLA. I have worked on software evolution, mining software repository, and software development tool. Then I moved on to studying data scientist, and then that really changed my heart. So now I'm focusing on debugging and testing and software engineering for data analytics and machine learning. And recently I was co-organized docs tool on software engineering for machine learning.
Okay, thank you very much, everybody. Now we're going to do some very quick run-through overview of your research, 4 minutes at max, and then if you run more than that, I'll have to shut you down, and then we'll go to the Ask Me Anything participants to ask us anything. So who's first? Christian.
You want to go in the order of slides?
Yes, please.
All right. So I come to this from a teaching perspective, and I'm interested in how software engineering changes if you introduce machine learning components into kind of a larger software system. So this is specifically not training models, kind of the data science perspective, or building a machine learning framework. And it's also, I'm thinking more about systems that end users use or that companies use, not the kind of things that you see at these conferences where we as software engineering researchers use machine learning for all kinds of tasks to do interesting things like improving code completion. But it's really end user software or big systems with a smaller or bigger machine learning or AI component, like Microsoft Office introduced the automated slide designer mechanism, right? So this is a heavy machine learning project where people spend a lot of time figuring out how can we automatically learn from data to make better looking slides. And it's integrated in this larger system. So it's a software system with a machine learning component. And there are probably a bunch of things that change when you build this. And you need data scientists and software engineers and probably all kinds of others like business people and operators to work together. To just grossly simplify this, data scientists and software engineers tend to have different backgrounds and they tend to have different educations and things that they focus on. So very simply, data scientists often work with fixed data sets and they work on improving accuracy and building a model, but at least kind of in education, typical classes don't tend to focus much on actually deploying these things or running this in production. Whereas software engineers, which I guess you all know, focus much more on actually building products, are concerned about kind of trade-offs and qualities and process and all these kind of things, right? And to build software projects with an AI component, you need both, right? So you need to think about how to build a system, a larger system, not just the model. And there are lots of challenges that kind of change in software engineering if you introduce machine learning or AI, like missing specifications, feedback loops, and so on and so on. But there's also lots of things that software engineers can bring to the table. We have a lot of experience of kind of engineering trade-offs and limited resources and knowledge and bring a system perspective and requirements engineering. Like just thinking about the world versus a machine is probably very useful to think about feedback loops and so on and so on. So I see this that in software engineering, we kind of have a spectrum from simple systems to more complicated systems. And we have methods for all of these, right? So we have the more heavyweight methods that you use when you build safety critical complex systems. And kind of many AI systems fall more into the complex system category. So I think we actually need to think about how to build this. So before Tim shuts me down, so my pitch here is that, yes, there are lots of research problems and lots of things that we need to improve. But I think, first of all, we need to understand, we need to teach people to think about software engineering when they're building these systems, not being that naive and kind of using and adopting all the methods that we already have. Mohammed?
All right, great, thank you. So I want to build on what you just said, Kristen. I wholeheartedly agree on the principles and the skills that every different discipline brings to the table. And as you said, like the complex system is hard because every time you create a new one, it's a new beast versus a complicated system that you once figured out it is containing so many steps, but is something you can repeat over and over. AI belongs definitely to the complex systems. And that's why we think of computing with data and thesis of this book is basically maximizing the overlap, right, between the two circles that you had, people coming from a data science background and people coming from software engineering background. And there's this skill gap between not just like implementation wise, but understanding, right? So when we think of AI computing systems, you really are building a tool or building a solution. And if you were coming from the software engineering background, you're usually doing something on the big data side, or building some back-end system for indexing, maybe pipeline for training. You really need to understand how it's going to be utilized, right? So if I tell you like I want to build this like gadget, you have to go and do your market research and understand how the user is going to use it, and vice versa. When you're thinking of modeling and you're thinking of like, I'm going to build this amazing, very high accuracy model, you need to understand the implications when the bits hit the metal. Like, how is this going to translate in terms of efficiency, in terms of cost, and other things that you have to worry about when you're building this at scale. So next slide, please. Very quickly, we advocate for a new breed of data. You can see here that the data that we have been talking about in the past before, the data sets have been what we call like CRUD operations, right? Like you do some databases and you have some records that are just sitting there for the sake of like archival and retrieval. Today, it's really the new code. So if you think about like how we implement a machine learning system end to end, a lot of it is in that big formula that does the inference, right? And we train the models to get to that. And if you think of the entire stack for software, how do you actually get to build software, and how do you get to reap the benefit of the software? You start with the hardware, of course. And I think we are in a place now where hardware for AI software is specialized. It's done in a way that is beneficial for the AI researchers and engineers who are doing the inference. But I also think, even when you look at the higher levels of the stack, there's some more love for the frameworks that are focused more on math and probabilistic programming. But I assume or predict in the future that it's going to be even more love for them. And the places where we're missing a lot of the ecosystem is the collaboration space, where if you think of GitHub and what it did for software, open source solutions specifically, of course, there are some solutions and places where you can go contribute software repositories and whatnot. But the sheer volume of repositories and the simplicity and just the ease of using GitHub allowed a huge explosion, right, in the way that open source came together. And I can see something very similar starting to happen right now. Like, call it Data Hub, call it whatever you want to call it, but there are a lot of places where you can see people coming together and contributing to DAGs, for example, like a way of having a workflow that manages the data for you, and version controls the data and so on. So if you think of something like DVC or dagshub.com, these are projects.
So thank you, Mohammed. We have to keep moving.
Okay, thank you. All right, go ahead.
Okay, so I will build up on what have been introduced so far. So my take on software engineering for AI is more a system engineering problems. Next slide, please. So as we know, building a machine learning-based systems involve additional activities that are not very common in traditional software engineering systems. So in addition to implementing components that describe the logic of the system, we have additional activity that have to do with cleaning data, extracting features, training the model, monitoring the model, deploying the model. So all this additional challenging of making those models ready to be integrated in the system in which they coexist with traditionally built systems introduce additional challenges for which I think we need to update some of our engineering practices. Next slide. Yes, so just to visualize it, so traditionally in traditional software system, we move from our requirement. Once it's clear what we want our component to do, we want to implement a system, we write down the rules that govern the behavior of our system. But in machine learning-based component, things goes from the data. So from the data, we extract the rules, features and rules that will, through inferences, next slide, please, leads to the system, next slide, there's an animation, functioning. So this change in logic, this inversion in paradigms make it more challenging to reason about the behavior of the system. So there is an additional complexity in making sure that a system built by this inference mechanism is satisfying our intended goal, providing guarantees on the behavior of the system, testing that the system is robust and not functioning properly. So there's an additional complexity that comes in introducing machine learning that's component in the software system. Next slide, please. If you look at the space of issues in a traditional based systems, it's much more wider for a machine learning based system than a traditional based system. So in a machine learning based system, you can have issue with data, noising data. You have issues when you train your model. You also have issues, I have an animation, please. You also have issues when you're actually implementing the mechanism that is needed to train and generate and inference the model. So the space of issue that you have to deal with is much more broader and wider than in the case of traditional software systems. So although, as Christian mentioned, we already have many interesting techniques in traditional software engineering that we can leverage and build from, I think there is some need of adapting some of these techniques to cope with this new reality. Next slide, please. Next. So all in all, I think the space of issue of maintaining machine learning-based system is much more broader than traditional software system. In addition, for the issue that we have to deal with traditional system, we have data-driven modeling issues, integrations issues, deployment issues that comes an additional complexity when we introduce machine learning based system in the software system. And for that, I think we have to revisit and build some of our. This is my case here.
Myung, you're muted.
All right. Let me start from my takeaway message. Like, I think as a researchers who've been focusing on like mining software repository, maybe we need to also like move and expand our focus to build the research techniques that, enhances like data analytics. So software engineering for data analytics. So in preparation for ASC keynote last year, I analyzed over 300 papers from 4 years of ASC proceedings. And then I found that a lot of our research in software engineering fields has focused on applying data analysis techniques to code recommendation, defect prediction, and other kinds of software evolution problem. But only 4% of the papers are actually targeting improving or enhancing or adapting software engineering techniques to target these new breed of machine learning based systems or data analytics application. So next slide. Some of you in the audience may think like, what does data scientist mean? Or how is it really development in this today's world different? Is it just a buzzword or, just a trend? To deeply characterize this emerging workforce of a data scientist, I actually conducted in-depth interviews with the data scientists and surveyed almost 800 data scientists in collaboration with the Microsoft Research. Next slide. And what we learned from these studies of a data scientist is that traditional software development is significantly different from data-centric development, both in terms of process and also the challenges that developers and testers and product managers face. Data is huge and remote and distributed. Writing test cases is really hard. Failures are hard to diagnose, define, and debug. And also these systems are very complex and make it difficult to debug and trace like provenance of data because the frameworks and system stacks and hardware support is very complex. Next slide. So with my students at UCLA in the past 5 years, I have built like automated testing and debugging techniques for big data analytics application, in particular written on top of Apache Spark. And this experience taught me that it is very challenging to not only define what is the correct behavior for heuristic-based and predictive analytics or probabilistic software, but also providing these debugging and testing techniques require us, software engineering research community, to work together with the AI, ML, and systems, big data systems, and database systems community to build this sort of a traceability support and adapt the existing debugging and testing techniques to these new complex domain. All right, so that's my short intro. And then Tim, you can take it over.
Okay. So one thing that's exciting in this new age of virtual conferences is that we actually have advantages in this new format. One of them is the voting system in Slack. People are asking questions on Slack and people are voting for those questions. So following on from our distinguished chair, Sarah's example in a previous talk that I saw, will we asking questions in the order of the voting. So if there's something you're excited about, please upvote that and we can focus on that. And I think that's a real advantage of this format. Our current highest voted question comes from Sarah to Mohammed. Did you notice that data scientists who work with who are actually lacking SE knowledge? You're wondering what the industry's view is on education and what should we be teaching our students who might be working more and more with ML systems. So we'll start with Christian on that one, because I'm sure he's got some very strong views on that. And then we'll move to everybody else. Christian.
Let's ask Mohammed what he wants his employees to learn.
Let's ask Mohammed.
All right, so it's a good question, because if you think of the skill set that has been for software engineering for a long time, you hear what you prepare for in an interview, like algorithms and problem solving and all of these. the mindset has been shifting. When you're talking about like data science, you still have these traditional requirements, let's call them that, like intellectual horsepower, right? The ability to go and figure out something that is ambiguous and chart, a course for it. If you're looking for somebody who's senior, like also doing this for a larger scope. Now, when you talk about data science specifically, there's the ability of sifting through heaps and heaps of data and seeing what others missed. And then there's the communication part, which is usually neglected in the way that you train these data scientists. They have to go talk to decision makers and sometimes actually change their minds, right? So the ability to have the evidence of data, but also the credibility and the way to communicate are extremely important. I still think that there's a lot of skills that we can go through, like the tools and different frameworks they have to know. But in essence, these are the two big things for data science. And if you talk about machine learning, you can add on that the ability to see this in production when you get real data from the real world, right? Out of domain data. How do you do domain adaptation? How do you understand the covariate shift in production? And what do you do to correct it and these things? And then some of the theory for debugging, like when you understand like there's something wrong with my model, what do you do, right? So observation or observability of the model, and then going into the details and debugging it. I think this distinguishes a great machine learning engineer and data scientist from the others.
Very good. Other panelists?
Yeah, I want to share some of I actually want to clarify that, it's very important for us to talk about data scientists as a subcategory, not as a single group. One of the things that we have noticed by doing survey was that data scientists are actually very different in terms of working style, the time that they spend, and also very distinctive in terms of skill set. So of course, there is a skill gap or education background differences between data scientist population from software engineering population. But what really differs, it depends on the subcategory of data scientists, whether they are coming from, whether they are machine learning engineers or whether they are like the statisticians who are more familiar with the like RStudio or more step package type of work, or the people who build like data pipelines such as on top of Apache Spark or Apache Hadoop or other kinds of big data storage. So, I might be waving a lot of hands, but I just want to say that it's not a single group, right? And understanding that subgroups are actually really important.
And I don't have a formal study like Miriam, but we talked to a bunch of engineers in places about what we should teach, right? And I think a common pattern that we saw is that especially startups and smaller companies, they tend to hire data scientists and then they build models and then now what, right? So kind of putting things into production, like the entire DevOps thing is something that's common, thinking about architecture, thinking about requirements and risks. I think those are all good things to teach from my perspective, kind of mostly system thinking actually, like, has been said before. Right?
Yeah, so just to double up on that and maybe share a bit on experience. So recently in March, we run a winter school here in Montreal with Ivado on bringing machine learning based application in production. And most of the participants to the school were actually data scientists, like they were in the industry, higher in different companies, building models and training models. But the big issue that they were facing was actually to be able to put this model in production and integrate them in the application ecosystem of those companies. And that was a skill gap that they had. So I think when we're training our students, if they are coming from a more data scientist background where they are savvy in training modeling and calibrating the model, I think they need also to understand the challenges of integrating this in a software system, testing this, building them, bringing them in production, monitoring the behavior of this model and so on. And I think if we also have some machine learning engineers that comes from the software engineering background, it's important for them to also be exposed to statistical modeling and the other, because it's difficult to test what you don't understand. Right? And so they need to go beyond using libraries and really understand the inner theoretical fundament of the inference mechanism so that they can actually be able to catch when there are issues maybe in their training model so that they can actually be able to build a high quality system. So I think there's some need of complementarity make sure that the workforce that we are sending in the industry is ready to put those applications in production.
So that raises the issue of testing, which is our next most popular question, which we'll ask in just a second. I point out that many of the people on this panel have been actively involved in this very question for a long time. Myung organized an excellent Darkstuhl seminar, which we just got in before the COVID pandemic shut down the world. And I've posted to the Slack channel an excellent post-Darkstuhl report that Christian wrote, where he wrote down some interesting views on machine learning, requirements engineering. And I just asked Myung when the next report from the Darkstuhl thing will be available, and that's in progress, and we should see that at some time in the near future. Our next question is, how do you debug machine learning models? For example, sometimes the new data you add cause your model to become worse. What data versioning help with that would help to roll back the previous data inputs or other functionality like that? So any other panelists about testing and debugging machine learning models?
So I think there has been some work by Xiangyu Zhang's group and several people. So there was a recent debugging of machine learning models workshop at ICML, specifically within machine learning community. But echoing some of the opinions from the Darkstuhl participants as well as a data scientist I studied in industry, it's not just a model debugging problem or identifying data that's leading to the faulty or unexpected model behavior. Often the question is much broader in a sense that it's about debugging systems that invokes this machine learning model, right? So I think, just to summarize, existing work often uses some of the mathematics or statistics or to identify faulty data that's responsible for unexpected behavior of the model. But in practice, the problem seems to be broader scope than just model debugging.
Myung, you had an excellent good news story. Your keynote at ASE 2019, you gave a story where debugging the scripts that did machine learning was actually crazy easy, not crazy hard. Can you take a minute and explain those results?
So just a sort of segue, with my students, we have done, set of research on translating automated debugging and testing techniques to big data analytics. So it's not just a machine learning, but big data ingesting application. One we found is that once you build a sort of debuggability or traceability into these big data system stack, as a kind of re-engineering runtimes and framework, because the big data systems are very, data application tend to take longer. Once you build the traceability into the system, we can significantly reduce the time. The other result that Tim might be mentioning too is that even though big data analytics application looks very complex because data is big, the application in terms of, let's say, control flow or set of path conditions in symbolic execution that we're familiar with might be still very small subset of a problem that we can simplify. So I think what I want to say is that we don't have to be scared of the complexity of a big data analytics application. It has inherent unique challenges, but in the end, it is actually logic that's developed by a human engineers, right? So I think once we get a handle on abstraction, we might be able to simplify these problems, right? With some of the insights coming from abstraction and software engineering.
Other members of the panel on debugging.
Maybe I can chime a bit on this. So recently with one of my PhD students, Hussein, who actually attended Darkstuhl run by Medium early in the year, we have been looking at debugging deep learning training programs. So instead of generating data inputs that will try to uncover corner cases in the final trained model, what we're trying to do is to debug throughout the training process to spot for issues, whether or not the learning is progressing correctly, whether you have a vanishing gradients and other. So what the approach we took in this it's a property-based approach. So we review the machine learning literature about the property of the different functions and the inferences that come put in contribution in training the model. And he mostly designed a framework to watch the training process of the model epoch after epoch and assessing certain properties. And this way we can actually uncover many of the pitfalls that have been reported in some of the recent software engineering papers that mine issued from Stack Overflow, that experienced by developers actually trying to train deep learning models. So I think it's possible, but that's required, in my opinion, a deep understanding of the machine learning training process, identifying what are the key properties that could be indicators of something going wrong during the training process. And capitalizing on that, we can actually build, in my opinion, effective debugging techniques to actually prompt and notify someone training a model that is actually experiencing an issue. So that's could be one way also to improve the quality.
Mohammed or Christian?
Yeah, I think, go ahead, please.
So for debugging, there are lots of different things that you could debug, right? And even thinking about what a bug means might be problematic depending on where you see the scope. I think a useful thing to look into for finding issues in models, like whether they behave correctly, what people tend to do is a lot of stuff that's actively explored in the interpretability work in the machine learning community, right? So kind of trying to understand what the model does, so you find it in a way that you can actually understand behavior, that you can understand patterns, instead of just looking at input-output pairs. So there's, I think, a lot of useful behavior, and a lot of this is very similar to work that we did in the software engineering community on specification mining, invariant mining, and things like this.
Yeah, I wanted to add the black box nature of a lot of the deep learning models make it such a hard challenge. Some of the times working with like computer vision makes it a little bit easier because you can do some stuff like you see patterns and error classes. And I think for that, error analysis is extremely important. So debugging before you release the model into production is something, and debugging a problem that's in production is a whole different issue. But if you think of like having, curated a challenging data set for testing, then you can start doing error analysis and you will see, okay, maybe my model is unable to detect that that's a cat because it's like scaled differently or because it's, positioned at the corner of the image. So coming up with a covering sample of tests will help you debug issues. And then once you started seeing issues in production, you augment your test set with like similar issues. So you have kind of a regression test, if you want to use that analogy.
Fantastic. I was at the seminar that Mil Young ran early on this year, and I was worried we were too scared about machine learning testing. If we go back to 1995 and say we're going to replace waterfall methods with agile processes, everyone would say we're too scared, we can't test those systems because there's no requirements at the front. And yet years later, we seem to be very comfortable with agile and continuous. So I worry that we worry too much. I think there's a lot of really good news stories about our success in this area. But that's just my view. Philip Leiter once asks, testing, it feels testing AI is a lot more like testing non-functional properties, which is something we're not particularly good at. So any comments from the panel on non-functional properties?
So based on my experiences, like these machine learning systems are often probabilistic and has some non-determinism in its behavior, and performance is a huge issue. So it is true that the focus of testing may go beyond functional correctness, right? Having said that, I think some of the existing research on like testing, let's say deep learning based system has focused on mostly like proposing new test criteria such as like neuron coverage or like many different kinds of layer coverage and providing more metric. I do definitely see the need of a sort of a reinventing or redesigning end-to-end like sort of testing efficiency and then expanding its scope, right? If you ask me, what is it exactly, how is that different from prior work on like non-functional testing, I actually don't have an answer. I think that's a worthy question to ask as a researcher.
Do other panelists have a comment on that?
Well,
I think Go ahead,
agree.
please.
Well, I mean, I mostly agree on that. Right? I think our techniques for non-functional testing are not as mature enough, which is why actually testing machine learning-based system is actually even more challenging. Right? So I think we need to contribute more, in my opinion, in this space, because I think when we build a system with machine learning component, we don't expect the component to be 100% accurate or 100% precise. We know that there will be limitations. But what is important is to understand the weaknesses of these components so that in the system view, we can compensate for this when we're building the system. So we really need to test the boundaries of what this component is able to provide us as services, test for the robustness and other non-functional properties to be able to ensure the quality of this. So it's critical in my opinion, and we are not yet very good at doing this, at least for what I know, but I think this is the area where we need to put more effort.
So my comment was going to be like, I don't necessarily agree with the statement in the question, which is, I feel like most of the testing goes directly towards the functional properties of the system. You have to have very clear requirements going into this, because at the end of the day, you're trying to solve a problem, and even more so, you're laser focused on the problem in machine learning, because you're not just solving for a field of problems, right? We just agreed that there's always a narrow scenario that you're after. So if you think of the example I used before, which is the cat detector, it's not going to work in all situations because of the non-determinism, but you also don't say I have a solution for all of object detection. When you're going in, you're laser focused on one problem, and you have to have a clear set of requirements, a clear set of what is it that goes into my test data set. And of course, robustness is going to come up after you start seeing success and people want to use it in different situations. So if you think of speech recognition, for an example, right? It is difficult in the sense that you do not want to have so many scenarios for your model to handle. You want to focus on one or two scenarios that you're really good at and go after them. And that's why the domain or the scenario matters, and hence the function requirements.
So to sort of chime in and be, okay, go ahead.
I think Christian did a long post.
Oh, right, sorry.
I mean, this is all over the place. This is hard to answer in a few minutes or seconds, I think. First of all, there's a question, what are you testing? Are you testing only the model, or are you testing the entire system, which is completely different, right? Then are you testing in some sense with an offline data set, or are you testing in production with user data and telemetry, right? So there are huge interesting design questions there. I think back to the original question, I think unit testing is a weird analogy for just checking the accuracy of a model, because a single incorrect input is not a failure, right? Or a single incorrect prediction. In that sense, actually thinking about kind of performance testing as an analogy where you have kind of probabilistic properties or kind of vague properties you repeat multiple times, might actually be much more promising than thinking about unit testing, at least at this granularity of a single input-output prediction thing. But I think it really depends on how you look at this, and I think there is no good agreement on on testing terminology even.
Oh, yeah, I interrupted you. I'm sorry.
Oh, okay. So I wanted to sort of be controversial and say that Mohammed said, they are laser focused on the problem. But from software engineering researchers' perspective, that even task of detecting a cat, that's a clear high-level description. But when it comes to sort of low-level, what about like twisted cat? What about rotated cat? It's very hard to define what is a correct behavior. And some of us who comes from more formal logic method kind of background, just not being able to write that precisely in a language that we could all agree upon is really what it means by challenge, right? So in some sense, how do we write expected test result, right, for end-to-end system for given subset of let's say images or telemetry or log data, right? Because if people could specify very precisely, we would have encoded it as a deterministic algorithm, right? So
yeah, this is actually the core of what we were talking about before. It's the job of the data scientist to find the covering sample in the distribution that you want to solve for. and talk to the business leaders and understand like, what is it that you're actually trying to solve for? That's exactly the core.
So I feel I'm a bit at odds with the opinions of the panelists here. I used to write a lot with Tom Zimmerman about data science, and we used to say that the only good answers are the ones that destroy the questions. The constant in the agile world, we're constantly refining what the product is. In the machine learning world, we're constantly coming back to the business users with new insights from their data. And really, the best possible result I have is I go back to the business users and they say, oh, we need a fundamentally different approach. It usually happens that you go to the data with question 1, you can't answer question 1, but there's but that raises interesting business issues about question 2. So I find myself jumping across questions and not having well-defined specs and being completely happy with that. And yet the rest of the panelists seem to want rigid specifications all the time. So I don't quite know what to do with that. Maybe I'm just deluded.
There's a difference in the sense that you mentioned, which is perceptual tasks versus recommendations and insights. I think both are correct.
Can you say that again? Perceptual tasks?
Perceptual tasks. Like if I show you an image and say, detect the objects, that's an objective problem, right? Like you and I, there might be a small disagreement, but for the most part, we can agree on what are the objects in that photo. But if I show you an article and ask you summarize it for me, that's a very subjective, maybe gaining insights from an article. So both are valid, depends on the scenario and the use case.
Okay. Comments from the rest of the panelists, or?
Tim, I don't necessarily view that the future lies on being able to specify precisely using some logic or better domain specific languages. I think maybe future lies on, as you said, being able to iterate quickly, right? Or visually describe or quickly kind of give feedback on what people can do. So it's not necessarily that we have to bring our existing ideas in software engineering or some of the formalism directly into this domain, but sort of augment, facilitate, and build some sort of scaffolding so that we can do these debugging and testing in this new domain.
So if I may comment, so I think when we bring a product, we bring it to production, we need to get to have or to at least build a certain confidence that the system would behave at least in a certain expected way, right? So although we may not have precise specification of what the system have to do, we still need to be able to test that there won't be unexpected behavior beyond the boundary of what is considered acceptable for this product. So in this sense, I think we need to be able to derive mechanism to test for this and to be able to track for drifting when we're drifting away from this subject.
But I do hope we end up with a agile data science and not a waterfall data science. So I hope we can go to that. We are at a panel on MSR. So I feel obliged to ask Bogdan's question, which is, what are some, if any, MSR specific insights that could help with SE for ML? Any comments from the panel?
I think one interesting observation is that a lot of the production machine learning that we're talking about, building system, happens closed source, right? So it's not easy to study large open source corpuses. So people have done this on notebooks, kind of the early data science stage, and on kind of pipelines and tools and so on that we're using. I think there's lots of challenge or interesting opportunities if you work with a company that actually has a lot of data science internally. So I think you're probably biased with the larger companies that have lots of kind of data science teams inside. I think there's a challenge of getting access to production machine learning to study this, but I think once you have this, there's lots of opportunities to see whether there are certain practices that lead to better outcomes, things like this.
Anything for anyone else?
Yeah. So my take is, I think to train and produce those models that will bring in production, we actually end up writing a lot of codes, right? We have write codes for machine learning pipeline for extracting data, processing them. We use different libraries to train the models and so on. So all this code, like any code, it's buggy sometimes, and maybe more often than we think, right? So I think many of our machine learning MSR techniques that we have been building and developing over the years can actually help a lot here as well, to help debug issues, track issues, detect issues in this code, which is, from some of the recent studies that have been shown, usually poorly written so far. So machine learning, space, data scientists, they actually need to start enforcing best practice in writing these codes. So far, there is no clear guideline on how these things should be done to be efficient, to ease their maintenance, to make sure that they are of decent quality, bug-free, and others. So there is a lot, in my opinion, that our community has to offer here to actually solidify this, I wouldn't say emerging, but this maturing software, in my opinion.
One of the advantages of this format is the ability to drop resources down into the Slack channel. So I'm hoping people are putting in interesting resources. There's been a request for Christian to drop in more resources on some of his material. I'd recommend to anybody Christian's website for teaching machine learning and SE. It's a fantastic resource, and I'm hoping Christian can share a link to that in the chat channel here. Just to drive the conversation to other places, there's been some questions about fairness. What would we do to make machine learning more fair? And Christian just posted a link to his site. It's a really good resource. Thank you, Christian. So fairness, what can we do to make AI SE fairer or more unfair? Worst and best practices for fairness.
I think the best that we can contribute as software engineers is in the requirements engineering stage. So fairness is a challenging problem, right? So this has been studied a lot in machine learning and philosophy and in many other fields. And there are lots of notions, different notions of fairness, and lots of criticism of each single one of them. And it depends a lot on the context. So you really need to figure out, what are you trying to achieve? What do your stakeholders want? And this is really where a requirement engineer is in the right position to go out and talk to the stakeholders, synthesize different notions of fairness, which one is appropriate, what do we need in the system? And then later we can do some testing and actually apply the methods and so on. But I think the key thing that people don't focus a lot on is really this requirements engineering role, figuring out what are the requirements in terms of fairness, notions of fairness of different stakeholders for the system.
Yeah,
I just want to chime that actually Yuri Braun and several other people have worked quite a bit on for testing fairness. So, you know, actually it would be interesting to hear their perspective. They're not here yet. But I don't necessarily think this, I mean, of course, the requirements engineering is a big deal, but I don't think it's just like being able to write what fairness means, right? I think, you know, testing is, testing is about like contrasting whether, like, given certain input, how descriptively different, how different from this other input, right? Like, I think maybe that was sort of the Yuri Braun and other people's angle on it, right? So
from my perspective, the testing part is fairly straightforward and fairly solved once you have the specification, right? So you just produce input outputs, you have challenges of producing representative inputs and so on. And there's a lot of work on this, right? So once you have the fairness specification, ensuring or testing whether the system meets that, I think there's a lot of work that we can adopt fairly out of the box. I think figuring out what are the fairness requirements is much, much harder.
So I actually agree with that, because just last week in our webinar, we had a talk about many philosophical blind spots of this fairness issue. It's actually very challenging to specify what is considered and make sure that we pick all the potential fairness problem in a software system. So I think requirement engineering, in my opinion, I'm not very much expert in that, should probably help. And I think once we have that, we can actually operational testing for this property. And there are some libraries in the machine learning community and different techniques that people are proposing to try to address some of the bias, whether from the data point of view or in the model training point of view and others. But for this to be very efficient, I think it's important to really identify what we want to mitigate, what we want to ensure. And I think that in itself, from what I know so far, it's challenging.
I think there's also room for some canonical tests that if you think of like certain domains, computer vision, speech recognition, like these tasks that deal with like human input, right? There might be room for us to actually come up with references, right? And this is actually something that we can borrow. And I agree with your point earlier that we don't have to start from scratch. There's a lot of things that we build for traditional software that we can start thinking about in the light of machine learning. So the great thing about all of these repositories that we have on multiple websites, that you can have a huge data set to glean from best practices. So you're kind of leaning on the wisdom of the masses of like all of these repos, and you're saying, oh, I see like 99% of GitHub repositories that are written in Python do testing this way. And then you can start thinking of like, here's a best practice we agree, add it to the canon or not, right? Same thing we can do in machine learning. Like here are the collective wisdom of the models that have been doing this. Is figured out like where do they have shortcomings, address them if we don't agree with the shortcomings, and if we have like good practices, we just add it to that benchmark and ask people to like, please score it on your benchmark for fairness, or this kind of like challenging benchmark for this task. This will allow us to get like a comparison or a list of tools and frameworks that will go feed the model examples that are agreed upon, that this is how you measure fairness for, like maybe there's some bias in the data and you want to figure that out before you even release it, and you want to avoid any downstream embarrassment.
So Fatouche mentions a fairness toolkit. The standard one used a lot is the IBM AIF 360 toolkit, which I put a link into. Myung mentioned Yuri's work. If he was here, I'm sure what he would say was, if you build, data can support multiple models, and the models have different criteria. If you don't control for certain criteria, such as the false positive rate between different reserve populations, it's a random variable if your model will satisfy that criteria. So he's doing hyperparameter optimization at runtime, including those fairness goals, so that when you build your models, you're actually building models that are fair. And the kicker there is, if you look at the IBM, the AIF 360 link I posted, they have up to 70 definitions now of fairness. And so now we have this fun problem of optimizing for 70 different things, because like intelligence, fairness is something no one knows how to define. We have one question that's been shouted at now 16 times. Is it better to train a software engineer with lots of development experience, or is it better to get a data science and train them on software engineering principles? Any comments from the panel?
I think I can jump on this one because that's the thesis of the book I mentioned before, Computing with Data. We need both. You got to come from both extremes and see the other side. There's a lot of value to bring the two skill sets into the same room and like figure out what is it that you want the system to achieve, put in the foundation of like the design and bridge that gap. But I don't think like there's one better than the other.
I agree.
I echo that. We talk at the same time. So when I did the studies of 800 data scientists, what we saw is that, lots of people are coming from, let's say, bio statistics and like, experimental physics and like economics and finances, a lot of like data heavy discipline. But what we are also seeing is the category of what we call as a moonlighter, the traditional software engineering, computer science background, but moving more and more into data analytics, machine learning, AI, incorporating that as a kind of part of their daily work, right? So, and if I looked at the number quantitatively, actually moonlighter is actually a very big population. I believe that that's actually going to grow even more, right? But we really need the both. And what they need in terms of help or like skills that supplement are of course different because of the kind of training that they have had to, before joining the project, right? So.
Yeah, I echo that. I think we need both, and I think depending of their strengths, they can contribute in different stage of the release and production process. But to be efficient, they really need to understand both spaces of the problem.
So yes, you need both, but from everybody I talked to, it sounds like it's much easier to teach a software engineering person some data science than to teach a data scientist software engineering.
Well, maybe we should try at the undergrad level to try to sprinkle those both dimensions in our program.
Yeah, I think the right solution is to have some awareness on both sides and have interdisciplinary teams, right? And you see a lot of software engineers who want to learn about data science and get more awareness this way. I think the bar is higher to encourage data scientists inside companies to want to learn about DevOps or something.
So we've just run out of time, and that's a great final point. I'm going to do one last post in the Slack. Young had a great survey of the skill sets seen at Microsoft for people doing machine learning and software engineering, and that might give the audience a sense of the broad range of skills needed to successfully do this. I wish there's one bad thing about this format. We can't hear everybody clapping. So if people just drop a clap into the Slack so we can hear the volume. I'd like to thank our great page turner Christian. I'd like to thank our speakers, and I'd like to thank you all for participating at MSR 2020. Stay safe. Black Lives Matter. Welcome to the new world. Have a great virtual day.
Thank you, and hopefully see you in person next year.
Right. Thanks so much.